Hello, good morning. How are you all? I hope you all are fine. Oh, I hope you all are perfectly fine. Okay, let's start with today's video, which describes the nature of the singularities, and we are going to discuss some of the expected examples which are very important, which describes the nature of singularities. So let's start with the assignment 1. Before starting the assignment, we have to recall some of the remarks which are very useful, and also these remarks are very useful in UGC NET exams. So let's start with the remarks. Here, first one is the formula which is given to us. Sin z minus cos z is equal to root 2 sine of pi by 4 minus z. Can I write like this? If you open this sin a minus b, the formula which you're having, so when you solve this formula, then you will get back your sin z minus cos z, right? So this is sin pi by 4 cos z minus cos pi by 4 sin z. If you solve this and then multiply with root 2, you will get back sin z minus cos z. Similarly, sin z plus cos z is equal to root 2 sin pi by 4 plus z. Second, this is very important one. The limit point of a sequence of poles of a function fz is non-isolated essential singularity. We have already done the proof of this theorem in the earlier videos. You can check that out. Third is, if limit z tends to a, f of z is equal to infinity. If limit comes out to be infinity, then the function has the pole at z equal to a. So for the poles, we are having the limit as infinity, right? And if limit z tends to a, z minus a into fz, if this limit is not equal to 0 or infinity, then fz has pole of order 1. Because here the power is 1, so the pole is having the order 1. This is your simple pole, right? And if limit z tends to a, z minus a the power n, f of z is not equal to 0 or infinity, then fz has pole of order n. So here the power is n. Then if the limit not comes equal to 0 or infinity, then you are having the pole of order n. Then is, if your limit z tends to a, fz is equal to infinity, then fz has a pole at z equal to a, right? If limit z tends to a, fz does not exist, then fz has essential singularity at z equal to a. And if the limit exists finitely, then a is your removable singularity. So whenever the limit comes out to be infinity, then that function is having the pole at z equal to a. And if the limit does not exist, then the function is having essential singularity at z equal to a. And if the limit exists but finitely, then the function is having removable singularity. But if you want to check the order of the poles, then you have to apply this limit on z minus a into fz. And if this limit is not equal to 0 or infinity, then you are having the pole of order 1, and pole of order 1 is your simple pole. And if it here the power 2, then you are having the pole of order 2, right? So now we will be starting our example. Find the singularities of the function fz is equal to 1 over sin z minus cos z and describe their nature. Now here the function is given 1 over sin z minus cos z. Can I have the formula for this? Yes. Just now we have studied in the remarks that we can write 1 over sin z minus cos z as root 2 cos of z minus, it is sine. So root 2 sine of z minus pi by 4. So because we have to discuss the nature of the singularities, let's check whether this function is having essential singularity or not. And for essential singularity, we know that limit does not exist, right? So at which point the limit does not exist? Now here, if you take your z tending to infinity here, then we know that sine of infinity is not defined, and this function is not defined at z equal to infinity. So can I say that z equal to infinity is my essential singularity of this function? Yes, because at z equal to infinity function, the fz does not exist. So since limit z tending to infinity, fz does not exist. So z equal to infinity is an essential singularity. Don't confuse up if you thinking of putting z equal to 0 over here, because for z equal to 0, the function will be sine of minus pi by 4, right? And we are having the value for sine of pi by 4. So the only one value where the function does not exist is z equal to infinity. So this is my essential singularity of fz. Now we are going to check for poles. For poles, the limit should comes out to be infinity, right? And where I got the limit as infinity, if my denominator, the points where the denominator is 0, I'm having those points as my poles, right? So let's think of my z where the denominator will be 0. That means your sine of z minus pi by 4 should tend to 0. And let's check at what points I'm getting for z so that this limit comes out to be infinity. So for poles, I have to take my denominator, means the denominator should be 0. That's why I will get my function to be as infinity. So this implies, now where sine of z minus pi by 4 is equal to 0, add sine of 0. So can I write it as 0 to be sine of 0? Yes, which implies z minus pi by 4 is equal to 0. And of course, we are also not having 0 at 0, but also at n pi, right? So I'm writing here n pi, which implies z is equal to n pi plus pi by 4. You can put n here 1, 2, 3, 4. For all the values of n going to the integers, I'm having my sign as 0, right? For all n belonging to integers. Now, since limit z tends to n pi plus pi by 4 f of z, let's check. This is limit z tends to n pi plus pi by 4. What is my function? It is 1 over root 2 sine of z minus pi by 4. Now if you put the value over here for z, I'm getting sine of n pi, and sine of n pi is 0, which means 1 over 0 is infinity. So I'm getting the limit as comes out to be infinity. So at what point my limit comes out to be at infinity? At z n pi plus pi by 4. That means fz has poles at the point z equal to n pi plus pi by 4. So therefore fz has poles at z equal to n pi plus pi by 4. So I got all my poles at z equal to this n pi plus pi by 4, right? Now to check the order of the pole. How to check the order of the pole? For that we are having the formula that limit z tends to a, z minus a into fz. If this limit is not equal to 0 or infinity, then we can say that I am having the pole of order, whatever order I am having. So let's start with the order 1. So I am taking my point to be as where I am getting the poles at this point. So put limit z tends to n pi plus pi by 4. Z, this is your a. So I am putting in bracket z minus a. So a is this. So this is n pi plus pi by 4. Z minus a f of z. Let's check this limit. This is equal to limit z tends to n pi plus pi by 4 into z minus this, z minus n pi minus pi by 4 over root 2 sine of z minus pi by 4. Now if you put the value of z over here, you will get 0 by 0 form, right? And now I'm going to use the L'Hopital's rule over here. Differentiate the numerator and denominator with respect to z, and you will get limit z tends to n pi plus pi by 4. What is the differentiation of the numerator with respect to z? It is 1 only over. Now the derivative of sine of z minus pi by 4 is root 2 as it is. So this is cos of z minus pi by 4. And now if you put the limit over here, I am getting cos pi by 4, which is this is equal to, okay, pi by 4 cancel. I am getting cos n pi. So this is 1 by root 2 cos of n pi. Now for the odd values of n, I get minus 1. For even values of n, I get plus 1. So this is plus minus 1. So can I write it as 1 over root 2 minus 1 the power n according to your n. So this limit is not equal to 0 or infinity, right? So this limit is not equal to 0 or infinity. That means I'm having the pole of order 1. I'm having fz to be as a simple pole of order 1 because here the power is 1. So I will say that I'm having fz to be as pole of order 1. So fz has simple pole at z equal to n pi plus pi by 4. I'm writing here fz has simple pole. Next, third, I have to check whether it is having non-isolated essential singularity or not. For that, we have to go back to the theorem that in the remark we have studied. The limit point of sequence of poles is your non-isolated essential singularity. Now, if you check this limit, as n is tending to infinity, z is tending to infinity, right? As n is tending to infinity, z is tending to infinity. What are the poles we are having? What are the sequence of poles we are having? The sequence of poles we are having are, yes, at z equal to n pi plus pi by 4, right? Pi plus pi by 4, 2 pi plus pi by 4, 3 pi plus pi by 4, so many infinite number of poles I am having, right? Now what is the limit point for these poles? We have to take the limit. So as limit n tends to infinity, z is also tending to infinity, right? So z equal to, that means z is your limit point. Z is the limit point of this sequence of poles. So z equal to infinity is a limit point of the sequence of poles of fz, and according to the theorem that the limit point of the sequence of poles of fz is your non-isolated essential singularity. I have also written this theorem as a remark in your recalls at the very beginning of this video. Keep this again and again in your mind. So z equal to infinity, I got my non-isolated essential singularity at z equal to infinity. So this is a non-isolated singularity, essential singularity of fz. So here ends up. So this is how we describe the nature of the singularities if any function is given to us. There is an exercise for you. The same question is this. Find the nature of the singularity of fz equal to 1 over sine z minus cos z at z equal to pi by 4. Now here the point is given at z equal to pi by 4. The whole of the proof, the whole of the solution is similar. You just have to put z equal to pi by 4 everywhere and you will get your fz having a simple pole at z equal to pi by 4. Of course, you will get a simple pole at z equal to pi by 4. You can calculate. Thank you very much. Next time again we will discuss some more examples which describes the nature of the singularity. Okay, thank you.